Yes, so welcome for our second talk today. So it's by Hongming Nie, and he will tell us about zeta functions and entropy for non-Archimedean subhyperbolic dynamics. So please.
Okay, thank you. Okay, it's my pleasure to talk in this seminar. So today I'm going to talk about some recent work with Jiang-Chung, Hsia, and Chenxi, okay, about the zeta function and entropy for non-Archimedean subhyperbolic dynamics. Okay, so let's first fix some notation. So let's consider some complete valued field K. Okay, it's associated with some absolute value. Okay, usually we assume this absolute value is non-trivial. Then we say K is non-Archimedean if this absolute value satisfies the strongly triangle inequality, which means the sum of two elements, the absolute value of sum of two elements in the field is less than or equal to the maximum of the absolute value of each of these two elements. Okay, there are many non-Archimedean fields. For example, the p-adic numbers QP, CP, and the Laurent series over C, or the completion of the formal Poisson series. Okay, over C. So the difference between the Laurent series and the formal Poisson series is that okay, the Laurent series is not algebra closed. Okay, if we consider its algebra closure, we can get the Poisson series. Then we take completion, and we get the completion of the formal Poisson series. So these two fields, the Laurent series over C and the Poisson series over C, are very useful in complex dynamics. Then the first four field has characteristic zero. Okay, but the first two has, the residue characteristic zero, residue characteristic P, and the third one and the fourth one has the residue characteristic zero. Okay, then we also have some, some uh, characteristic P non-Archimedean field. Okay, we can consider the FP then joined with some transcendental element T and consider the Poisson series or Laurent series, then take the algebra closure. Okay, then this is also an interesting non-Archimedean field. Okay, so this is examples for non-Archimedean fields. Then for the Archimedean fields, so we can consider R and C. Okay, I think we are all familiar with the real numbers and the complex numbers. Okay, so now we have this field. So now we can, okay, as what we did in the complex numbers, so we can consider the projective line over the field K. Okay, so a property for the in the non-Archimedean case is that if the K is non-Archimedean, then the projective line is totally disconnected. Okay, this is not a good property, but okay, to fill out the gaps, so we can use the Berkovich projective lines. Okay, this is developed by Berkovich, so and also used in the study of the degenerating in complex dynamics. Okay, but in this talk we will not use the Berkovich line. Okay, we only consider about the projective line or K. Okay, so the non-Archimedean property implies that okay, if we have two disks in the field, okay, then if these two disks intersect each other, then one disk contains the other. Okay, this is a very strong property. Okay. Okay, now let's consider a rational map over K. Then this rational map defines a dynamic system on the projective line. Okay, here we always assume the degree is at least 2. Okay, then we have the dynamical system, we can consider the periodic point. Okay, then a point is periodic if there exists some integer n such that some positive integer n such that under the iteration, under nth iteration, this point goes back to itself. Okay, similarly, then we can define the repelling periodic point. We only require the multiplier has absolute value greater than 1. Okay, then if periodic point is not repelling, we call it non-repelling. Okay, here let me give some notation. We consider the okay with the fixed k the phi to n for the set of fixed point of the instant interval of phi, which is exactly the periodic point of period n. Okay, and we use the fixed star k phi to n for the set of repelling fixed point of the instant interval of phi. Okay, then the fixed star k phi n is a subset of the fixed k phi n. Okay, this is about the fixed point. Then we can also discuss the Fatou set and the Julia set. Okay, the Fatou set is the maximum domain of the equicontinuity of the integration of the map on the P1K. Then its complement is the Julia set. Okay, then by this definition, it's obvious that the Julia set is forward invariant. Okay, then we get a induced dynamic system on the Julia set. Okay, so this is a basic. What happened here? Okay, now let me state some properties for the Julia set and Fatou set. Okay, especially when the K is non-Archimedean. So the first one is that all the non-repelling period point is contained in the Fatou set. Okay, this is very different from the complex case. Why is this true? Because the non-Archimedean property implies that if we have a fixed point, non-repelling fixed point, okay, if we consider the point nearby this point, if we compute the difference of the 2 points, then we can say the difference does not change. Okay, this means nearby this non-repelling period point, we have the equicontinuity. Okay, and the second one is, okay, when the K is algebra closed, then the Fatou set is always non-empty. Okay, but when K is not algebra closed, then the Fatou set could be empty. Okay, it depends on the field and definitely depends on the field and depends on the map. Okay, but the Julia set could be empty, no matter whether the field is algebra closed or non-algebra closed. Okay, for example, there's a very large class of maps called the maps having a potential good reduction. For such map, the Julia set is always empty. Okay, then we also have the closure of all repelling periodic points is contained in the Julia set. Okay, this is by definition. Okay, but at this moment I think we only know the Julia set is contained in the closure of periodic points for general rational map. Okay, this is proved by Hsia. But the good thing is that if phi has a repelling periodic point, then we know the Julia set is exactly the closure of the repelling periodic point. Okay, but for general rational map, I don't think so. We know the repelling density. Okay. Okay. So there's some properties for the Fatou set and the Julia set in non-Archimedean case. Okay, now let's consider the Artin-Mazur zeta function. Okay, here we want to use the periodic points. So okay, we can consider all the periodic points, and we define the zeta function as the zeta function is defined by the exponential of this series. Then the coefficient is the number of the fixed point for phi n divided by n. Okay, so then this in dynamics we know this one this zeta function is rational when the K is algebra closed with characteristic 0. Okay, it's proved by Hakkinen in 1994 for the field when the field is complex numbers, and it's extended to the non-Archimedean case with characteristic 0 by Lee. Okay, however, here I should say when the characteristic of K is positive, then this zeta function could be translated. Okay, here I should remove this residue. Okay. Okay, some example was studied by Brandy. Okay, this is for the uh, all period points. Then okay, we know the rationality or transcendence for the zeta function. Okay, then we may ask what happens for the repelling period points. Okay, now we define the zeta function to consider the we define the zeta function by the repelling period point. Okay, by number of repelling period points. Okay, then which is the exponential of the sum of the number of repelling period points of period n divided by n times Tn. Okay, then when the field is C, we know that all the number of all the I mean we know there are only finitely many non-repelling period points. Okay, then this implies in this case this zeta function is also rational over Q. Okay, then in other words, it's clear in the complex case. Then what about the case in non-Archimedean? Okay, here so the non-Archimedean is very different from the Archimedean case. For example, it's not hard to construct some polynomial with non-empty Julia set having infinitely many non-repelling period points. Okay, but in this case, I mean the easy part is to construct such a polynomial having okay infinitely many indifferent period points, but only finitely many attracting period points. Okay, but but it's also possible to construct some polynomial, some non-Archimedean polynomial with non-empty Julia set having infinitely many attracting period points and infinitely many indifferent ones. Okay, this is not easy, but there is such an example. For example, Benedetto gives such an example. Okay, the phase Z is 1 over P, Z to P plus 1, plus P minus 1 over P times Z to P. Okay, acting on CP. Okay, this is a polynomial, and Benedetto shows, okay, this polynomial has a non-empty Julia set and having infinitely many attracting period points and infinitely many indifferent period points. Okay, then for this map, for this polynomial, if we work on the zeta function defined using the repelling period point number of repelling period points, we see that this zeta function is transcendental. Okay, this is transcendental. Okay, so now we may think, okay, could we get some rationality result for some special map? Okay, for some special map. Okay, here let's consider the non-Archimedean subhyperbolic maps. Okay, here we assume the K is non-Archimedean. Then we say a rational map is hyperbolic if the Julia set contains no critical point. Okay, so this definition is different. I mean, different from the complex case, because in complex case we may have the parabolic point, right? Parabolic period point. Then even though in that case, even though there's no critical point in the Julia set, but it's still not a hyperbolic. But in non-Archimedean case, then all the indifferent cycle is contained in Fato set. Then okay, to define the hyperbolicity, we only require the Juliet set contains no critical point. Okay, similarly, we can define the subhyperbolic maps. Then a rational map over K is subhyperbolic if each critical point in the Julia set is eventually periodic. Okay, this implies if a map is subhyperbolic, then each Julia critical point eventually maps to a repelling cycle. Okay, then if we think about the Benedetto's example, this phase A. Okay, we can find this map has two critical points. One is 0, which is a fixed point. Okay, that's another one which maps to and the iteration goes to infinity. In other words, this polynomial is hyperbolic. Okay, this shows if we consider the zeta function defined by the number of repelling period points, then even for polynomial, even for hyperbolic polynomial, then the zeta function could also be transcendental. Okay, so now our main result says that, okay, now let's consider some non-Archimedean hyperbolic rational map. We assume this real set is non-empty and compact. Okay, this is important. The real set is compact. Then the zeta function is rational over Q. Okay, so I should mention that for Benedetto's example, then the Julia set on the Julia set in CP is not compact. It's not compact. Okay. Okay. So then okay then in fact this there are lots of non-continuous subhyperbolic maps having compact Julia set. For example, if the space P1K is compact, then the Julia set is automatically compact. For example, if K is a finite extension of QP. Okay, but in other case, even though the P1K is not compact, but the Julia set could still be compact. Okay, such an example is given by Hsia and Truk. Okay, for example, for some polynomial, if the polynomial in the shift locus, okay, here the shift locus is the same definition as in the complex case. Okay, all the credit point goes to infinity for polynomial. Okay, then this for such polynomial over non-Archimedean field, then such polynomial has compact Julia set. No matter the space is compact or not, but the Julia set is compact in such case. Okay, there are some other examples. Okay. Okay, now okay here now let me give the review of how to prove this result. Okay, then okay because we assume the Julia set is compact, then we can consider some covering of this Julia set such that the each element in the covering is either a scale disk or a point, and this point is in the forward orbit of the Julia cradle point. Okay, here scaling disk means okay we have a disk, and for any 2 points in this disk, if the phi acting on these 2 points, then the distance of the image and the distance of the 2 points is scaled by some factor, and this factor is independent of the points in this disk. Okay, then this covering contains countably many elements. Okay, countably many elements. Okay, now this countably many elements may not satisfy the Markov property. Okay, then we should separate these elements. Okay, we should separate the scalar disks to get some small disks. Then we get a new covering satisfying the Markov property. Okay, but by this splitting, so we in fact get a topological conjugacy between the Julia set away from the ground orbit of cradle point to the symbolic dynamics of countable in many states. Okay, this idea is also used by a police paper with Fan Liao and Wang. Okay, to study the Julia dynamics for the non-Archimedean subhyperbolic maps. Okay, so okay, now here we get a covering containing countably many elements and satisfy the Markov property. Now we should do one important step. Okay, then okay we should do the factoring. So okay, now we have the symbolic dynamics with countable states. Okay, then we want to get some symbolic dynamics with finitely many states. Okay, then here we consider fractaling induced by the natural equivalence of the orbit of the disks. For example, let's look at this green box. Now here I draw a point P. Let's assume this point P is a repelling fixed point. Okay, then there's some disks in the K near this point P. Okay, because P is a repelling fixed point, then under the integration, the nearby disks will map to some other disks also nearby, maybe select far from the point P, but some disks. Okay, then we can consider some for some very large iteration. Okay, then we get for very small disks near P, but not contains P. Then this disk under the iteration of phi to M maps to some disks. They map some disks. Okay, then we identify this this sequence of disks in the same orbit of phi to M as one element in the symbolic dynamics. Okay, in the new symbolic dynamics, then we can do this for all the disks nearby the point P. Okay, then by this way, then we get a symbolic system of finitely many states. Okay, here I use sigma b. Okay, so in fact this sigma the Julia set and the sigma b has a very strong connection. So this means there's a map there's a map G from the Julia set to the to sigma b such that G is a topological conjugate on the Julia set away from the ground orbit of the correct point. Okay, moreover, the complement of the image of G in sigma b contains finitely many period points, finitely many period cycle of the sigma. Okay, okay. Later I will give you an example which is be more clear for this argument. Okay, now okay, here we will relate the non-Archimedean the Julia set to the sigma b. Okay, then we can use the zeta function for the symbolic dynamics to to get the zeta function for the Julia set. Okay, in fact we can write down the zeta function for the Julia set precisely. Okay, we get the zeta function is exactly some product product of finite many terms 1 minus t2 Lm divided by the determinant of I minus tb. Okay, then the numerator and denominator may have some common factor. Okay, may have some common factors. Then we can simplify this quotient and get the zeta function. Okay, but this shows the zeta function is rational. Okay, now let me give you some example. Okay, so let's consider the k. Okay, let k be the maximum unramified extension of qp. Okay, let's consider the polynomial, the cubic polynomial, phi z, which is z times z minus 1 squared over 8p. Okay, then we can find its correct point is 1 and 1/3, and 0 is a repelling fixed point. Then 0 is in the Julia set. Then the correct point 1 maps to the fixed point 0, and the correct point 1/3 goes to infinity and integration. Okay, this calculation shows this map, this polynomial is hyperbolic. This one is hyperbolic. Okay, now, okay, now a fact. Okay, a fact here. I don't want to give the proof, but a fact shows so the Julia set for this polynomial is compact. Okay, it's compact. Now we can consider some disks D1 in the disks which has a distance up to a value of p from 0. Okay, so we can consider D1. Then we have D1. There exists such D1. Okay, such closer disk D1, such that D1 and maps to the D1 p up to value of p and phi. Okay, we can find such D1, and then we can find inductively we can find Dn. Okay, we find Dn. Okay, then similarly, so for okay, then we want to find the pre-images of Dn. Pre-images of Dn. Okay, then the preimage of Dn, one preimage is the Dn plus one, but it has two other preimages. Then we denote by Bn plus or Bn minus. Then when the index for the D is odd. Okay, but when the index of D is even, there's no such preimages because in our example the K is not algebraically closed. Okay, we may miss some preimages. Okay, here. Okay, this is I mean, this is a messy picture, but I want to use this picture to give the orbit of these disks D1, Dn, B1, Bn, Bn plus and Bn minus from Berkeley review. Okay, here just draw a tree, then each point in the tree, in fact, corresponds to a closed disk. Okay, for example, this point. Okay, I mean, sorry, this one. Oh, what should I do? Okay, let me see. What should I do? Okay, maybe. Okay, this one is a D1. It's a disk D1. D1 bar. Okay, the closed disk. Then it has three preimages. This one, and this guy. Okay, but for D2, it has only one preimage because the field K is not algebraically closed. Okay, has only one preimage. Okay, similarly, for the D3, we have three preimages. This guy, and some others. Okay, and the one, sorry, the one here. Okay, so this gives the orbit of this these disks. Okay, so now here I draw. Okay, sorry. Now here I draw this portrait for the orbit of the corresponding disks. Okay, then we know. Okay, oh sorry. Then we know the D2n plus one goes to D2n D2n minus one, then goes to D3, D2, D1, and then D1 maps the union of Bn plus Bn minus and one. Okay, then the Bn plus and Bn minus is also preimages of D2n minus one. Okay, then you can see this is countably there are countably many disks, and this disk covers the Julia set. Okay, here now we want to use this countably many disks to get a symbolic dynamics of finite many states. Okay, what should we do? So we should collect the D2n minus one, all the D's with odd index as a new simple. Let's say denote it by alpha plus, and all the disks with even index, all the disk D with even index as a new simple alpha minus. Okay, then similarly we write the beta plus is all the Bn plus, and the beta minus is all the Bn minus. Okay, then we have four simples for all these disks. Okay, then by the the orbit of these disks, we can get this finite graph. Then we have alpha minus goes to alpha plus, and alpha plus goes to alpha minus, right? Because the D with odd index goes to the D with even index, and the D with even index goes to the D with odd index. Okay. So then we also have the alpha plus goes to beta plus, and the beta plus goes to alpha plus, right? Because the D1 goes to all others, all the B's, and the B goes to the D with other index. Okay, we also have for example the alpha plus goes to beta minus, and the beta minus goes to alpha plus. Okay. Okay, but we also have the alpha plus goes to one, and the one goes to zero, right? Because one is the critical point, and zero is the depending fixed point. Okay, so 0 goes to itself. Now we have this finite graph. Okay, then we can write down the corresponding the transition matrix. Okay, B here. Okay, then this B is it only contains the each entry in this matrix is either 0 or 1. Okay, either 0 or 1. Okay, so okay, now we should observe that. So for this two cycle from alpha minus to alpha plus for the two cycle. Okay, this two cycle is in the sigma B, but this is not in the Julia set. Okay, because this two cycle corresponds to the D with even index goes to D with other index. Okay, we get two cycle. But in the Julia dynamics, this disk cannot give us a cycle. Okay, cannot give us a cycle. Okay, so this means when we use the symbolic dynamics when we use the symbolic dynamics with finite state to code the Julia dynamics, we get some extra part. Okay, okay, but when we compute the zeta function, then we can remove this extra part. Okay, then for this example, we know we can do directly the zeta function is 1 minus t squared divided by the determinant of I minus tb. Okay, this is the determinant I minus tb is from this symbolic this symbolic dynamics sigma b, and the 1 minus t squared is for this actual two cycle. Okay, then we can plug the matrix B and calculate directly. We get this is 1 minus t squared divided by 1 minus t times 1 minus 3t squared. Okay, then we can cancel the common factor of the numerator and denominator. We get 1 plus t over 1 minus 3t squared. Okay, this gives us the precise formula for the zeta function. Okay, as you can see, so this expression and this expression for the zeta function in this example satisfies the general formula for the zeta function. Okay. Okay, good. So this for zeta function. So okay, now once we have zeta function, then we can get the entropy, right? We get the entropy. Okay, because under the assumption the hyperbolic, subhyperbolic, and compact real set, then we know the topological entropy is the limit soup of the growth rate of the pure of the pure n the pure points of the n cycle. Okay. Okay, so this is the topological entropy. Then okay, then from a general result, so we know the topological entropy is in fact is the log of the reciprocal of the convergence radian of the zeta function. Okay, then the rationality of the zeta function immediately implies the entropy is a weak prime number. Okay, here a weak prime number is a real algebraic number whose Galois conjugate has I mean, so the weak prime number is a real algebraic number, a real algebraic integer whose so value is the largest one among all of its Galois conjugates. Okay. Okay, so now in fact there are lots of work studied entropy for non-chemical dynamics. For example, the for Rivera studied the entropy and the maximum measures for the Berkeley dynamics. Okay, they studied in the one-dimensional case. So they show that for most case, the topological entropy is log of degree of the map. Okay, but there are some special case which is the topological entropy is not log of the degree. Okay, but they also give some lower bound for the topological entropy. Okay, then recently the Fao, Chun, and Hsia they studied the higher dimensional case for Berkeley dynamics. they proved that the topological entropy is at most the maximum of the log of the arithmetic, the log of the dynamical degrees. Okay, then okay, as I mentioned in the first result, they showed that in most cases the topological entropy is log of the degree, but there are some special case. Okay, then the Benjamin and Benedetto and other authors provide such special case. Okay, they construct some rational map whose topological entropy on Berkovich space is not log of degree, not log of degree, but it's positive. Okay, the entropy is positive, but not a log of the degree. Okay, so I should mention that in the result 1 and 3, they require the field is algebra closed. Okay, algebra closed. And they okay, now all the results are considered the Berkeley dynamics. Okay. Okay, so okay, our result. Okay, now let me state our result about the entropy. Okay, so now we let K be a complete non-archimedean field equivalent with a discrete valuation. Then the set, okay, then the exponential of the entropy, okay, for subhyperbolic rational maps with compact real set, okay, then this set is equal to a set of weak prime numbers. Okay, as I mentioned, the theorem 1 tells us that the exponential of the entropy for any subhyperbolic non-archimedean maps with compact real set is a weak prime number. Okay, then to prove this result, we should show the other direction. Okay, which is that for any weak prime number, we can construct a subhyperbolic rational map with compact real set. Okay, so now let me give you the sketch of the construction. Okay, there are several key parts in the construction. Okay, the first one is we call it the admissible matrix. Then okay, let's see the definition. An n by n irreducible matrix A is admissible if okay there are no rows and columns that are identically zero and no zero entries, non-zero entries in each row are constant. Okay, so the first condition is I mean is very kind of trivial. Then the second condition, okay, okay, why we okay the reason we use second condition is we want to when we construct the map, we want the map has constant degree on each disk. Okay, then the third condition is that so if two rows share a non-zero column index, then the index of the non-zero column in one row contains such index for the other row. Okay, this is something like the like a non-archimedean property for the disks. Okay, so because we know if two disks intersect each other, then one contains the other. Okay, one disk contains the other. Okay, here is similar property. Okay, okay, if the two rows share a non-zero column index, then the index of non-zero columns in one row contains such index for the other row. Okay, then we also require some Markov property. Then for each I, there is an integer mi such that the ith row of the a to mi contains at least two non-zero entries. Okay, because this is a admissible matrix. Okay, then we show that okay for okay let lambda be a weak prime number, then there exists an admissible 0, 1 matrix with leading eigenvalue lambda. Okay, this means from a given weak prime number we can construct an admissible 0, 1 matrix. Okay, so how to do that? So Okay, let lambda. Okay, for this weak prime number lambda, then we know that exists some integer n0, so that the lambda n0, lambda to n0 is a prime number. Okay, then we apply the Lenz's theorem. Then the lambda n0 is a leading coefficient of a non-negative integer matrix B. And okay, for some integer G0, the B to G0 is a positive integer matrix. Oh, okay. Sorry. I should delete it. The table, I should delete this B. Okay, then this means, okay, for given weak prime number, we get some matrix B to G0, which is a positive integer matrix. Okay. And this B to G0 has a leading eigenvalue lambda n0 G0. Okay, but this BG0 is not a 0, 1 matrix. Okay, and it's also not a admissible matrix. Okay, then we should do some process to get a admissible 0, 1 matrix. Okay, then we consider graph induced by the BG0. Then okay, this is a finite graph. Then we should add some and more vertex on each edge. Then we get a larger graph. Okay, and we from this larger graph we can get an admissible 0, 1 matrix with the leading value lambda. Okay, in fact, for each edge we add n0 j0 many vertex. Okay, now this shows that for any given weak prime number, we can get an admissible 0, 1 matrix with the leading eigenvalue lambda. Okay, so now the second key part is that okay, we want to construct some piecewise linear map. Okay, here okay, we want to relate to the 0, 1 matrix to some piecewise map, some piecewise linear map. Okay, then given an n by n 0, 1 matrix A, then a map from n many disks to K. Okay, is linearly compactable to A if okay restricted to each disk, F is linear, and the dj is contained in F of di if and only if aij is 1. Okay, in other words, the matrix A encodes the image of F for these disks. Okay, then for any so for admissible 0, 1 matrix A, we show that exists a map F from n many disks to K, which is linearly compactable to A. Okay. In fact, we can in fact there's many such map F. We can choose F and the DI so that the domain of F and the disks in the domain of F is locked nicely. Okay. Now in this after this step, so for any given weak prime number, we get a piecewise linear map. Okay. Now here the next step is we want to glue all the piecewise linear map to get a global rational map. Okay, so I should mention that for this map F, for this map F, okay, on each disk it's linear, definitely it's a polynomial, right? Because it's a linear polynomial. But now after gluing, we want to get some rational map. Okay, to do this gluing process, we use this result. Okay, it's given by Clara, Praise, and Brodia. Okay, so okay, so in fact, the version we used is slightly different from theirs, but they have the same flavor. Okay, so now let's suppose we have this as many pointwise disjoint rational disks in CK. Then okay, we can pick any point in each of the disk, then we consider then we set the rho I is the distance between each of the two each pair of such points. Okay, then we pick any point bi of ck. Oh, here, okay, sorry, here I should mention that the ck is the completion of the algebra closed of k. Okay, if k is not algebra closed, then okay, then we pick a number bi in the ck such that the bi has some good bound. Then for some rational maps, for estimated rational maps, satisfying good properties. For example, the rational maps, the GI maps bi is a disk, okay, in CK, and the GI maps the union of all these disks is uniformly bounded. Okay, then we can construct a rational map Fz, which is the sum of GI times HI. Okay, the HI has a precisely formula here. This is 1 over 1 minus Z minus AI or BI of some power M. Okay, here M is a very large number. Okay, then for this rational map F, then this rational map capital F has same and almost the same property of the GI on BI. Okay, then we have the F maps BI is exactly the GI maps BI. Okay, and in fact, the difference between these two maps is very, very small. Okay, and they also have the same degree on the BI. Okay, then in our setting, so we have the from the given weak prime number, we get 0, 1 admissible matrix. Then from this matrix, we get a piecewise linear map F. Okay, now we want to glue. Okay, using the above result, we will glue this F and get a rational map F. Okay, but in the formula for this F, okay, there's some M. Okay, some very large number M. Okay, then we should choose this number carefully. Okay, then we can get some good rational map F. Then we show this map F in fact has coefficient in K. Okay, in general, this map F has coefficient not in K, it should be in CK. Okay, because we choose the BI in CK, it may not in K, right? But if we do carefully, we can get the F has coefficient in K, and F is hyperbolic. Then the Julia set is contained in the union of all these disks, where the disk is the domain of F. Okay, then this shows the F in fact is a hyperbolic map in K over K with compact Julia set. Okay, and this F is what we want. Okay, so the entropy of this map F is the log of the given weak prime number. Okay, here we further show we can get a hyperbolic map, not just a subhyperbolic, but it's a hyperbolic map. Okay, so this gives the proof for our second result about the entropy. Okay, here let me see some examples. Okay, so let's construct some hyperbolic rational map in Q2. Okay, with entropy is log 1 plus square root of 5 over 2. Okay, now let's consider this number 1 plus square root of 5 over 2. Okay, this is a weak prime number, then which is a leading eigenvalue of the matrix A 1 1 1 0. Okay, this A is already an admissible 0 1 matrix. Okay, now we want to construct some linear maps from this A. Okay, then we can, for example, we can consider F1 from the disk D1 absolute value of 8 to D1 absolute value of 2, sending Z to Z plus 3 over 4. And F2 is the map from the disk 3 absolute value of 4 to the disk of 1 absolute value of 4, maps Z to Z minus 1. Okay, so this A, the matrix A is 2 by 2. Then we have this two linear map. Okay, but in our construction, because we want to check the dynamics of the resulting map, then we also consider this F0, okay, which is the identity on the disk. Oh, sorry, 0, 2. Okay, here 2 should be the absolute value of 2. Okay, this F0 is used to help us to check the dynamics of the resulting map. Okay, now we construct the rational map physics. Okay, which is this one. Okay, now here we choose the this 14 is the, I mean, it's M here. It's M here. Okay, in the capital F, in the HI. Okay, we choose M is 14 in this example. Okay, then we get this rational map phi. Okay, now if this phi is a hyperbolic rational map, and its entropy is log of the 1 plus square root of 5 over 2. Okay, so as you can see, so this rational map has degree 14, which is very large. Okay, so we don't know how to construct some lower degree rational maps. Okay, then next example. So okay, we can consider some hyperbolic rational map or Q2 with zero entropy but a non-empty Julia set. Okay, this means we want the entropy is log of 1. Okay, then we can consider the admissible 0, 1 matrix A, 0, 1, 1, 0. Okay, then this matrix has a leading eigenvalue 1. Okay, which is a 2 by 2 matrix. Then okay, we can consider two linear map, F1 and F2. Okay, it's given precisely in the formula. F1 is a map from the disk to 1 absolute value of 8 to the disk 3 absolute value of 4, sending Z to Z plus 5 over 2. And F2 is a map on the disk 3 absolute value of 8, and sending Z to a point Z minus 1 over 2 in the disk 1 absolute value of 4. Okay, again, so we consider the F0, okay, which is identity on the disk 0 absolute value of 2. Okay, now we consider the map physics given in this formula. Okay, here now we will choose the capital M is 6. Okay, then we get this is a 6 degree 6 rational map. Okay, then for this rational map, then because our field is Q2, which is not algebraic closed, then we can check that the Julia set for this rational map is a 2 cycle. Okay, that's only 2 points. Then the Julia set is not empty, but the entropy is 0. Okay, entropy is 0. Okay, so this is some example. Maybe let me give you give a final remark. The Milner and Thurston studied the Artin-Mazur zeta function for interval maps, and they proved some rationality result. Then Thurston gave a complete description for the entropy of postcritically finite interval maps. Okay, so then in fact our statements are similar to theirs. Okay, but okay, there is a key difference. The key difference in the argument. So for the interval maps, because they consider the maps over R, then the interval of all the R has some linear order. Then we can use the orbit of the correct point to divide the interval in several pieces. Then we can consider the order of these pieces. But in and this order of the pieces gives some Markov partition. But in non-Archimedean fields, we don't have such order. Okay, we don't have such natural order. Then that's why we consider the disks nearby the orbit of the Julia set and do a more detailed argument. Okay. Okay, good. So I think I can stop here.
Okay, thank you. So let's thank our speaker. Okay, so are there comments or questions? Yes, Mitsu.
Can I ask a question?
Yes.
So Well, some elementary questions. Thank you for your talk.
Yeah.
So you define the hyperbolicity and the subhyperbolicity,
Yes.
but in the case of Archimedean complex dynamics, there are different characterizations like expansion on the Julia set, or
Yeah.
in the case of a hyperbolicity, you can use an orbifold metric.
Right.
So do you have a similar characterization in this setting?
Yes. Yes. We have similar. We have similar. Yes. Okay. So
So expansion or
expansion. Yes. Yes. For the hyperbolic map, that is expansion. So it's proved by Benedetto. But for the subhyperbolic, we can construct some singular matrix, then like the orbifold metric. Okay, we can do this, and we can show the expansion. Okay, this is a result by my co-author and myself. Okay.
but to define the orbifold metric in complex case, you use a manifold structure.
Yes. Yes. Yes,
And
but here we just construct directly. We
I
construct
see.
directly. Okay, we work on the neighborhood of the Julia gradient point very carefully. Then we can write down precisely formula for such a metric. Yeah.
Okay. Okay. Thank you.
Yeah.
Can I ask another question?
Yes.
So you said that Julia set can be non-empty but non-compact.
Right.
So
Right.
what's the difference? So what's the point in the difference? So if you take a closure of Julia set and subtract the Julia set, what are these points?
Yes, good. So one good question. So okay, if we consider the Berkowitz dynamics, okay, if we have a non-Archimedean rational maps, okay, if it's acting on the Berkowitz space, then the Julia set is compact. Okay, but in our setting, we only consider the projective space, which is the type 1 points of the Berkowitz space. Then the type 1 Julia set may not be compact. Then okay, if we want to consider the compactification of the type 1 Julia set, then we got a non-type 1 Julia point, which is in the Berkowitz space.
Oh, I see. So it's in the the Berkowitz space.
Right.
So
Right.
in a sense. Yeah.
Yes. Yes.
Okay. Thank you.
Yeah, thank you.
Okay, are there other questions?
Can I ask a question?
Sure.
Yeah.
Okay, great talk, Hongmin. Thank you. So, have you ever thought about a real zeta function?
Okay. Honestly, I didn't thought about it. I think Chenxi have some idea. Okay. My co-author Chenxi may have some idea, but I didn't
Okay.
think about this.